Okay, guys. So it says calculate the pressure needed to inflate a sphere that has a volume equal to that of the sun, assuming that the work done was 3.6 times 10 to the 34 power joules, and the sun's radius is 7 times 10 to the 5th power kilometers. So, the thing is that I have the books in different places. So this is the computer that I use for my virtual classes, and I don't have all the books here. So I wasn't sure if that was the exercise. Now, let me see. Okay, so they're giving me, it says calculate the pressure. That means that I need to find the pressure. Okay. The sphere has a volume equal to that of the sun. Okay. So assuming that the work done was, okay, they're giving me work as 3.6 times 10 to the 34 power joules. They're giving me the radius, that is 7 times 10 to the 5th power kilometers. So first thing I have to do is I need to convert those kilometers to meters, okay? So I can do it directly from my givens. In 1 kilometer, 1,000 meters. So in total, 5 plus 3 zeros is gonna give me 7 times 7 times 10 to the 8th power meters. So I have now the radius of my, well, of the sphere, okay? Because it is a sphere, it has a specific formula to calculate its volume. Remember that in this topic, we're going to need to calculate volume, or we're going to need to get the volume out of somewhere, okay? So there are many ways to get volume. You're going to use the one according to your needs, okay? So you can get the volume directly isolated from the formula, okay? If the formula is work equals pressure times delta V, so the volume is going to be work divided by the pressure. You can calculate volume as volume of a sphere because it's a known shape, okay? So you can calculate the volume of...
Miss,
Yes.
it's the problem is asking for the pressure.
Would you repeat, please?
We are looking for volume, and the problem said calculate the pressure needed.
Yes, I know. But you cannot calculate the pressure without knowing the volume. The problem is not giving you the volume neither, okay? So you need to get it from somewhere. So I'm giving you like the keys to find the volume in order for you to find the pressure, which is the main purpose of the problem. Belen, I saw that you raised your hand.
Yes, it's because in the work it says 3.6 times 103 to the fourth power.
The word problem, but the one I sent, I remember that I make the correction.
Okay.
In the problems that I sent to your group, I remember I make this correction, okay? And it should be, I remember I did it, okay? But I might be crazy. But it should be times 10 to the 34. I remember I did this correction in Paint. I remember, but I'm just going to check. Let me see. Just don't pay attention to this one from here, okay? Just pay attention to the one that is in the given. Or better, like this. Yeah. Okay, so I was telling you that there are many ways to get the volume. One, directly from the formula. If the formula was giving you work and pressure, you can get volume from that. Okay. If the word problem was giving you if the problem was giving you area and displacement, you can get the other formula for volume. Or because it is a sphere, sphere has a specific formula to find its volume. Okay, so a way to find the volume of a sphere is by using the formula that is a 4/3 pi radius to the third power. If it was a cylinder, you can use a cylinder. Okay, if it was a cube, for example, you have to use the formula of a cube. In this case, it's a sphere, so we can get the volume from here. All you need to calculate the volume of a sphere is to know the radius, which we already know. Okay, so from this, we say, okay, I don't have the volume, but I can get it. I use the formula, and I say, okay, the volume of my sphere is 4/3 pi. My radius in meters, because that's why I did the conversion already. 7 times 10 to the 8th power meters raised to the third power. And how much you got?
1.44 times 10^27.
1.44 times 10 to the 27.
Yes.
Meters to the third power are going to give you cubic meters. So once you have the volume, you can apply the formula to find pressure. Okay, so we say work is equal to pressure times delta V. You focus on pressure, so the isolation will be pressure is equal to work divided by delta V. And then all you do is you replace by your given work, that is 3.6 times 10 to the 34 power joules divided by the volume that you just got. How much you got? You can write it in the chat.
2 times 5 times 10 to the 7th
2
Pascals.
times 5 times 10 to the 7th. Thank you. 2.5 times 10 to the 7th power. These are pascals, and this is my pressure. That's the way that it had to be done.
It also can be 25 million square.
Yeah, the same. Any other question from the homework? No, right? Okay, thanks. Okay. So it says, a total of 135 joules of work is done on a gaseous refrigerant as it undergoes compression. If the internal energy of the gas increases by 114 joules during the process, what is the total amount of energy that is transferred as heat? Has energy been added or removed from the refrigerant as heat? So in this case, the problem is asking you, okay? The problem is asking you, what is the total amount of energy transferred as heat? So in other words, the problem is asking you, what is the heat? Has energy been added or removed from the refrigerant as heat? Okay, so when it says added or removed, it's going to be related to the sign. Remember what I said first. If you add heat, it's going to be represented with a positive sign. If you remove heat from a system, it's going to be represented by a negative sign. Okay, so this problem is giving me a total of 135 joules of work. So my first given are the joules of work. So they are giving me work 135 joules. It says this work is done on on a gas. Okay, it says done on a gaseous refrigerant. Okay, so basically is this work is done on a gas. And then it says undergoes compression. So what is the sign that we use for work when we talk about compression?
Negative.
Negative. Okay. So in this case, even if the problem doesn't give you 135 as a negative value, you have to remember that this is compression, and that compression is going to be denoted by a negative sign. So in this exercise, they're not giving me 135 joules of work. Instead, they're giving me negative 135 joules. Okay, that's my work. Then it says if the internal energy is denoted by the letter U. Okay, the internal energy, U, it says increases by 114 joules during the process. So 114 joules is my internal energy. It's going to be positive because it says increases. So they're asking me to find heat. Heat is denoted by the letter Q and is unknown. And according to the sign that we have, it can be positive or negative. So we can answer the second question as has heat been added or removed from the system? So the first law of thermodynamics says that the internal energy of a system is equal to heat minus work. Okay? So we need to find Q. Okay? Because we need to find Q, I need to isolate this work from here, which is subtracting. It goes to the other side to add. So you're going to have internal energy plus, okay, work is equal to Q. Okay, Amazing. It's not updating. Wait. Okay, so this is the isolation that you're gonna use to find Q. The internal energy, okay, we know it as 114 joules plus the work. The work given in this problem is a compression, so it's gonna be minus 135 joules of work equals Q. So this plus and minus gives you minus 135 joules. How much is this?
21 joules.
Negative 21 joules. Okay, what do we say with this? Because we have a negative sign, does it mean that the heat has been added or removed from the system?
Remove.
Removed, okay? Remember, added is going to have a positive sign and removed is going to have a negative sign. So we can say that heat has been removed. Why removed? Because of the negative sign, okay, from the system. And as you can see, the application is very simple. Now, thermodynamics is not this simple at all, okay? It's a lot more complex than that, but your book has very simple exercises.